Alright, so the last section here, number 20, well, before that, we need to be able to model with quadratic functions. And model in mathematics kind of just means take some type of situation and translate it into math. Make a model using mathematics. So we need to be able to know when we need quadratic functions, be able to model with them, and then interpret the results in the context of the problem. So here's like a very easy classic example. I hate to use the word easy, but standard example of modeling with quadratics. So some person standing close to the edge of the top of a building and throws a baseball vertically upward. The quadratic function S of t models the ball's height above the ground in feet t seconds after it was thrown. So there's the function, but if we even just think quickly, we got this person standing close to the edge of the top of a building. Careful, buddy. He's kind of levitating right now. Pretty neat. And he throws a baseball vertically upward. Well, I don't know about the physics involved in this question, but let's make his baseball baby blue. So he's throwing this baseball vertically upward, and there it goes. And so we know that it's gonna hit some height, and then it's gonna fall back down. Right? But apparently this function S of t tells the height of the ball if we know how many seconds it's been since the ball was thrown. Alright, simple enough. Question A. What was the height of the ball at the beginning of this problem? Huh? Well, let's think about that. We have this rule, and at the beginning of the problem, well, one of two things. We either are going to be given a height. Remember, this is the output. We're either going to be given a height and then asked to find time, or we're going to be given a time and then we can find the height. So let's go back and read that problem. Oops. What was the height? What was the height? So we need to determine height. That's what's unknown. Somehow the rest of this stands for time. The ball at the beginning of the problem. Well, how much time went by at the beginning of the problem? 1 second? Not quite. That would be 1 second later. What makes sense? 0 represents the time at the beginning of the problem. So when time is 0, that's when the problem started. So we need to make t 0 and then find the height. Input 0, put 0 seconds, and output comes the height. And by the way, what key feature is this? When you input a 0, if you said y-intercept, you got it. Alright, so let's do it. This is really the y-intercept. Input 0, s of 0 is negative 16 times 0 squared plus 64 times 0 plus 160. I love to use some color. Input 0, 0, 0. 0 seconds. What's the output? If you remember standard form, that makes 0, that makes 0. 160. 160 feet, since we're in the context of a problem. So at the beginning of this problem, the ball was at 160 feet in the air. Neat. Back to the other questions. And so just remembering, we are interpreting the results. So these are actually key features, but they have meaning in the problem. When does the ball reach the ground? When? That's asking us to find time. So we need to find time. Apparently, we have a height. The ball reaches the ground. We've seen problems like this before. When the ball reaches the ground, and this is sometime later, we don't know the time, but here it is. Well, actually, that's not on the ground, is it? but now it is. So how high is that off the ground? This height here is 0. It's 0 feet. Ah, we're finding an output of a 0. We're finding the zeros of this function. So here we go. S of t is negative 16 t squared plus 64 t plus 160. Man, those t's and plus signs look alike. So we got to be careful, but set this equal to 0 and find the solutions. So I'll make the plus sign a little bit smaller. 64t, space out my terms too, plus 160. And how do we find this? Oh, back to this trusty review sheet. We have standard form. We're looking for zeros. We can either complete the square or use the quadratic formula. I don't know about you, but I'm going to choose the quadratic formula. So you want to complete the square, go right ahead. Here's one little thing that I noticed. I can actually simplify this problem at the beginning. Didn't quite talk about this in class, but let's talk about it right now. What's one thing I can factor out of all these terms? Well, I think I can actually divide out 16. And I don't even need to factor it out. I actually have an equation. So if I divide both sides by 16, what's nice here is that this becomes 0. And, well, I will factor out the 16 out all these terms just to show you exactly what's going on. In this first term, factor out a 16, this becomes negative t squared. Factor out a 16 and 64. I know that that's 4 times 16. And this is obviously 10 times 16. Wait a minute here. So that's my division by 16. Those undo each other. And I'm left with 0 equals negative t squared plus 4t plus 10. Actually, let me show you another little trick or just thing to notice. I can see if this factors, however, I got to take care of this little minus sign in the front. So let me divide everything by negative 1. And if you don't like what I'm doing, go through and use the quadratic formula as is. The numbers are a little bit bigger. This will work out though. But if I divide this by negative 1, this term becomes positive, my middle term becomes negative, and my constant term also becomes negative. Can I factor this? Are there two numbers that multiply to negative 10 and add to negative 4? 1 and negative 10, 2 and negative 5. After all this work, this doesn't even factor. I need to use the quadratic formula. Well, it was worth a shot. See, sometimes it's better just to use the quadratic formula off the bat. But live and learn. Here's where I'm at. I did at least simplify my problem. I got rid of some of those bigger coefficients, just so you know what I did, by factoring out and then dividing by negative 1. I wanted to do that to see if it factored, but this doesn't factor over integers. So need to do a different method. Actually, completing the square doesn't look so bad, but I'll just use the quadratic formula. So our solutions are opposite of b plus or minus b squared, negative 4 squared, times minus 4 times 1 times negative 10, all divided by 2 times 1, which is 2. Alright, so let's do some simplifying. 4 times 1 is 4, times negative 10 is negative 40, minus negative 40. I don't know if you're catching that, but this right here makes negative 40. Always be careful with the signs inside here. So 4 times 1 times negative 10 is negative 40, minus negative 40 is the same as adding 40. Here's why I didn't factor, because this is not a pretty number, but that's okay. So we have 4 plus and minus the square root of 56 all divided by 2. And is this divisible by 4? Well, 4 times 10 is 40. 4 times 11 is 44. 4 times 12 is 48. 4 times 13 is 42. 4 times 14 is 56. Hey, it does. So 4 plus and minus 4 times 14 all over 2. Goodness gracious. 4 plus and minus the square root of 4 is 2. Square root of 14 over 2. And if I simplified my answers, I think in the numerator I have a common factor of 2. What happened inside there? Let's make that look like a 4. There we go, 14. And 2 times some number, then divide by 2 undoes. Oh, these colors are driving me nuts. So here's our answers. 2 plus and minus the square root of 14. This amount of time, so this is actually seconds, is when the ball hits the ground. Here's an application when we do want to use the approximation. We do want to approximate because most people don't know what that is. So let's go to a calculator and see. So 2 plus the square root of 14 is approximately 5 point, well, let's see, we're dealing with seconds, so I don't know what seems like a reasonable amount of rounding. Let's grab 2 decimal places. So this is 5.74. So approximately 2 plus the square root of 14 is approximately 2.74 seconds. And let's grab our other 0. I'm completely wrong, wasn't I? 5.74 seconds. My bad. So we're now at 5.74 seconds. My bad. And now 2 minus the square root of 14 is approximately minus this out here. -1. Oh, wouldn't that be nice? Negative time back in time. Wouldn't it, even for 1 second? Sometimes I say, man, I wish I just didn't say that. -1 seconds. Well, I don't even care about rounding because guess what? We cannot go back in time. So mathematically, this is a 0. In the context of this problem, though, you can't go back in time. So we just toss it out. This is totally legal. Just say it doesn't make sense in this problem. This is the only answer that does make sense. At approximately 5.74 seconds, the ball will hit the ground. So let's reiterate. Sometimes I need to go back and just review what we did. When does the ball reach the ground? When asks for a time. So that's what we're trying to figure out. So this represents a height. When the ball hits the ground, that's a height of 0. So using our function, set the height to 0. Here's the function. And then I noticed, I was trying to get clever for a second, that I could simplify this expression if I factored out a 16 and then divide both sides by 16. I kind of did that in a strange order, but still did it. It still works out. Yep, this is all legal. And then I thought maybe this would factor. Just thought maybe it was a trick question that it would factor. In order for it to factor, I need this to be 1, so I divided by -1, which changed all the signs of the terms. But after all that, it didn't factor. So if you were wise and at the beginning of the problem you just used the quadratic formula right from here with the calculator, you would have got to this final answer sooner than I did. But that's okay. Here we are, working the problem through. At approximately 5.7 seconds, 74 seconds, the ball will hit the ground. All right, moving on. What time? Again, we're asked to find a time here, so this must give us height? Does the ball reach its maximum height? Actually, we don't know the height, but we do have another keyword here, maximum. When does a quadratic reach its maximum? At the vertex. This means we must find the vertex. How do we do that? Well, given standard form, to find the vertex, take the opposite of b. That's really small, so let me zoom in. But you should have this yourself. But to find the vertex, you take the b value divided by negative 2a. Remember, that's the same as the axis of symmetry. And then we plug in, we substitute that value in, and there's your vertex. And that's going to be our maximum value. So let's do it. All right. New page. So we have this function s of t is negative 16 t squared plus 64 t plus 160. So b divided by negative 2a, which we did prove in class, gives us the axis symmetry, the x-coordinate of the vertex. 64 divided by negative 2 times negative 16. And this makes 32, which is 2. Alright, so our vertex, or likewise our axis symmetry, is x equals 2, comma, I don't know right now, but we'll use that value 2 and we'll substitute it into our function. So I'm going to kind of do things different here. Let me fill this in. Alright, so s of 2 equals negative 16 times 2 squared plus 64 times 2 plus 160. Alright, this is negative 16 times 4 plus 128 plus 160, and distributive property negative 40, negative 24, that's negative 64 plus 128 plus 160, which all works out to be, well, I'll take care of this. This is negative 64 plus 288. So 288 take away 60 is 228, take away 4 more is 224. That's the output. Remember, our output gives us height. So what did we just determine? At 2 comma 224, we have the vertex of this function. How do we interpret that? At 2 seconds, the ball reaches its maximum height of 224 feet. There we go. Probably should use a complete sentence here, but I'm happy enough with this right now. And that's it. And I think I actually answered the last question as well. What time does the ball reach its maximum height? Well, we just said that. At 2 seconds. And what is the maximum height of that ball? Well, I answered more than I needed to in this problem, because part C only asked me for the time, but I went through and found the height anyways. 224 feet is the maximum height the ball reaches. Can we check this another way? Yeah, let's do this on a calculator. We can't input x. We can't use t as an input variable on Desmos, but I'll call it x. So this was negative 16x squared plus 64x plus 160. On our TI calculators, we have to adjust the window screen, which takes a little bit of practice. We've been doing it in class. We will continue to do that. On this website, though, it's easy enough just to zoom out and kind of get a big picture. Actually, that It's not a great picture, so I do have to adjust the window a little bit. I can see just from this graph that I really don't need anything past negative, what's this, negative 50 and positive 50. So let me change the window a little bit to get a better picture. I want the minimum to be negative 50, the max to be positive 50. That's a little better. Actually, looking at this graph now, I know I really don't need to go anything less than negative 10. So let me readjust this one more time. And that's a better looking graph. So adjusting the window here, our zeros are negative 1.72, I'm sorry, negative 1.742 and 5.74. So remember, this was the zero we excluded because it didn't make sense. We can't have negative time, but that was the approximate that we found. So about 5.7 seconds. It reaches its maximum height at 2 seconds, and the maximum height it reaches is 224 feet. And initially, at 0 time, the ball was at 160 feet. So there you go. There's your key features of a quadratic: the y-intercept, the vertex, and one of the zeros. But in the context of this problem, 0, 160 represents the height of the ball initially. 224 represents at 2 seconds the ball reaches its maximum height of 224 feet. And the 0 here represents the amount of time it takes for the ball to hit the ground. So I hope you found this video helpful, reinforced some of the key features of quadratics, and good luck studying.